This is M0o, my Pywalls at Home 2022 entry. The overall design is a 1/14th scale imitation of a JCB telehandler commonly used in agricultural settings for moving hay bales and other heavy or bulky items around. It has all the main functional elements of a telehandler, but the stylistic aspects unfortunately took a back seat compared to completing the challenges. The construction uses laser-cut plywood and 3D printed parts, with the battery, power supply and motor drivers being enclosed in the middle of the chassis. It uses a 3S LiPo battery for power and has two dual H-bridge motor drivers, meaning that all four wheels can technically be independently driven, though I'm actually driving them in pairs for tank steering. M0o is driven by a Raspberry Pi Pico, which has two Cortex M0o Plus processors, hence the name. The Pico is many times slower and more RAM constrained than even a Raspberry Pi Zero, and so presents an interesting challenge in terms of processing power. The Pico has no wireless capabilities, so M0o also has an ESP32 to provide connection to a Bluetooth gamepad, as well as Wi-Fi for code upload and telemetry. For reprogramming the Pico over Wi-Fi, I had to implement my own bootloader, as it's normally programmed via USB. The ESP32 has no other involvement in the robot's processing, it is only used as wireless bridge. For sensors, M0o has a 9DOF IMU used for orientation, front and rear laser distance sensors, and a camera which is connected to the Pico via a shift register to save pins. The camera driver uses 4 PIO state machines and DMA to capture 80 by 60 pixel YEV images at around 20 frames per second, which are used to locate game pieces in autonomous challenges. The software for M0o is written in C and uses both cores on the Pico. Almost everything was written from scratch, with around 13,000 lines of new code for the Pico. Existing libraries are used for the laser distance sensors and some aspects of the camera configuration. M0o has an articulated telescopic boom made with a draw runner. A micrometal gear motor rotates a lead screw to extend and retract the boom, and a larger low-speed gear motor is used to raise and lower it. There are encoders used for feedback on both degrees of freedom and limit switches to enable homing. The boom control system uses inverse kinematics to enable precise control of the boom's position and trajectory. And a servo enables attachments to stay level as the boom moves up and down. Challenge-specific attachments bolt onto the boom and can have their own servos and sensors which connect to a M0o I/O expander. For some challenges, additional parts attach to the front of the chassis with magnets. For hungry cattle, a section of 2-litre bottle is used to hold enough grain for one trough at a time, with a servo-actuated flap for dropping the grain. This challenge is autonomous using the IMU to aim approximately towards a trough, then the camera and distance sensors to approach it. The robot returns to the barn autonomously, then pauses for refilling for each trough. For Nature's Bounty, an articulated apple picking attachment is used to individually pick the top 2 apples on each quadrant, dropping them into a bucket attached to the front of the robot with magnets. The picker has an infrared beam break sensor to detect the apples. The bottommost apple is simply knocked off by the back side of the bucket while positioning for the other 2. This challenge is also autonomous, using a combination of the laser distance sensors, IMU and camera to position the robot relative to the arena walls and the tree. Finally, for shepherd's pie, a grabber attachment is used to pick up the sheep in pairs and lift them over the wall of the pen. Elastic on the underside pulls the jaws shut, and a servo pulls them open with string, which avoids any issues with rigid linkages. A shover is attached to the front of the chassis with magnets to help with positioning and aligning the sheep. This challenge is completed via remote control. For the arena, I used the Cambridge Makespace Robot Club arena built by Brian Corteil. The challenge pieces are a mix of cardboard, laser-cut plywood, and 3D printed parts. Some parts are painted red to aid identification by my computer vision code, specifically the troughs and the base of the tree. Building M0o has been a lot of work, in particular because of the bare metal nature of programming for the Pico, but I'm pleased with how the robot turned out and how it has performed in completing the challenges.